Hello. Today we're going to look at the implicit function theorem. So if we're given a function f of x, y, z, then the partial of z with respect to x is equal to the negative partial of the function with respect to x divided by the partial of f with respect to z. And of course that's going to equal minus f sub x divided by f sub z. If you're unsure on this type of notation, then please watch my video on derivative notation. So similarly, you can have the partial of y with respect to z is equal to minus f sub z divided by f sub y. Okay, so the general combination you are looking at is the partial of a with respect to the b. You just simply do your cross. So b goes to the top, a goes to the bottom. Alright? So what we'll be doing here in this video is looking at some examples and comparing our normal implicit partial differentiation with the implicit function theorem. And finally, if we're given a function with two variables, f of x, y, then we say dy by dx is equal to the negative partial of x and the partial of f with respect to y. Okay? So, our first function is 4x squared plus yz is equal to sine of y times z. So, first of all, we're going to use the implicit function theorem. So, we want to find the partial of z with respect to x. So, the partial of z with respect to x is simply going to equal the negative partial of the function with respect to x divided by the partial derivative of the function with respect to z. But we haven't got a function, have we? We've got an implicit equation. So to get a function, we simply take away one of these expressions on one of the sides of the equations to get a function. So let's take a function f of x, y, z. This is going to equal the sine of y times z minus this term here. So it's going to equal 0. Minus 4x squared minus y times z. Okay, so you make the equation 0 and you simply put your function where the 0 is. Okay, so let's use the implicit function theorem. The partial of z with respect to x is going to equal the negative partial of the function with respect to x. So sine yz is a constant, that disappears. Minus yz is also a constant, that disappears. So we have minus 4x squared. If we differentiate that, we're going to get 16x. Sorry, 8x. Dear. Minus 8x. Okay. Now we divide that by f sub z. So we partially differentiate this function with respect to z. 4x squared is a constant, that disappears. So we're left with this. Sine yz and minus yz. So we need to use the chain rule. Differentiate sine, we get cosine. So we're going to get the cosine of y times z. Now we multiply this by the derivative of the inside. So y is a constant, and we differentiate y, the constant multiplied by the variable. We're going to get the constant back. So we're going to get y times the cosine of y z. Then finally we differentiate yz with respect to z, and we're going to get minus y. Okay, so all we need to do now is tidy this up a bit. We can get rid of the negative sign, and we can simply say this is equal to 8x divided by y minus y times the cosine of y z. Okay, so that's using the implicit function theorem. So what happens if you wanted to not use the implicit function theorem, but just simply partially differentiate implicitly this expression here? We should get the same answer. So again, we want to find the partial of z with respect to x. So what's our independent variable here? Our independent variable is x, dependent variable is z. So differentiate 4x squared, we're going to get 8x. Okay? Now we have plus yz. Now y is a constant, and again we're going to get the constant back, so we get plus y, but we have to put on dz by dx. You should already know this. If you're unsure about this, please watch my videos on partial differentiation and differentiation in general. Okay, this is going to equal sine yz. So like we did before, we got the cosine of y times z, and now we have to differentiate the inside. Well, we just did that. We got y partial of z with respect to x. So we multiply this by y multiplied by the partial of z with respect to x. Okay. So, of course, we have to factor. We want to get the partial of z with respect to x terms on one side of the equation. Okay. 8x, that doesn't matter. So all we need to do is bring this term here on the other side of the equation. So we get that 8x is equal to y minus the y times the cosine of yz, all multiplied by the partial of z with respect to x. And to rearrange to find the partial of z with respect to x, we just divide this term here. And finally, we get 8x divided by y minus y cosine of yz, which is what we got when we used the implicit function theorem. So in my opinion, the implicit function theorem is a lot quicker and a lot easier compared to your ordinary implicit partial differentiation. So another slightly more easier example is x cubed minus 5y to the 4 is equal to 7x squared minus 3y plus 6. And we want to find the partial of x with respect to y. Okay, so let's use the implicit function theorem first. We have dx by dy is equal to negative partial of y. Sorry, that's supposed to be an x. Partial of x. Okay? So let's do that. Dx by dy is equal to negative. So we have a function. Again, we need to get this in terms of a function. So I'll do this down here. So what do you want to do? Let's do f of x, y, z is going to equal 7x squared minus 3y plus 6 minus our x cubed, and then we add on our 5y to the power 4. Okay? So now we can use the implicit function theorem because we have a function. So partially differentiate this with respect to y. 7x squared is a constant, 6 is a constant, minus x cubed is a constant. So we have to deal with this. So partially differentiate minus 3y with respect to y, we're just going to get minus 3, and then we have this one here, we're just going to get plus 20 y cubed. Okay, now we divide that by the partial of the function with respect to x. Okay, that's a constant, that's a constant, and that's a constant. So we're left with 7x squared minus x cubed. differentiate 7x squared with respect to x, we're going to get 14x, and then we have our minus x cubed, differentiate that, minus 3x squared. Okay, so that's what we get. Now we can do it the other way. So x cubed minus 5y to the 4. For our normal partial implicit differentiation, we don't need to get it in function term, we can just have it like this. So again, we're trying to find dx by dy. So our y is our dependent variable, x is our dependent variable, y is our independent variable. Okay? So the derivative of x cubed, we're going to get 3x squared. Now we have to multiply that by the partial of x with respect to y, because our x is our dependent variable in this case. Okay, differentiate minus 5y to the 4. Of course, we're going to get minus 20y cubed. Again, differentiate 7x squared, we're going to get 14x, add on that dx by dy. Partially differentiate minus 3y, we're just going to get minus 3. Okay, 6 is a constant, that disappears. So we're left with this. Okay, so we want to get to this, obviously. So we can see that we add our 20y cubed onto the side and minus our 14x. We get, we get our dx by dy. Okay. Bring this negative 14x, so bring the positive 14x and make a negative 14x on this side. Multiply by 3x squared minus our 14x, all multiplied by dx by dy, is obviously going to equal our minus 3 plus 20y cubed. Okay, and therefore we get dx by dy. Dx by dy is going to equal minus 3 plus 20y cubed divided by 3x squared minus 14x. So what we got before was this, using the implicit function theorem. As you can see, we've got an extra minus there. So if we put a minus, if we multiply this whole equation by minus 1, we're going to turn these values around. So this is equal to minus 3 plus 20y cubed divided by 14x minus 3x squared. Okay, so we get the exact same value using the implicit function theorem and your normal partial implicit differentiation. Okay, so there you go. The implicit function theorem is really a neat trick for partially implicitly differentiating a function that may look really complicated using your traditional differentiation methods. So I hope that was useful for you, and I'll see you in the next video.